the last speaker of the morning is Bertrand Eynard from CRM, Saclay. And it's going to talk about geometry and integrability.
Yeah. Let me, sorry, I'm just, sorry.
You want to hide the side?
I should be able to do it in full screen. Can you see the full screen?
Yes, yes.
Okay. So first of all, well, thank you for inviting me. And I mean, of course, so I really hoped I could come in presence in Montreal. I hesitated. I mean, I was trying to find a way to come, but in the end, I could not. And I'm sorry, but yesterday I had an administrative meeting. I mean, I was very busy, but it's really a pleasure to do something for John. Well, I've spent many years in Montreal. We had lots of interactions with John, and we had really great interactions. We have made so many papers together. I spent a lot of time there. Well, just let me recall a little bit how I first met John. I was attending a conference about random matrices in CRM. And I think it was the time where John had discovered this duality in integrable systems, and he was trying to find something, I mean, some examples of application of this duality. And he met me during the coffee break, and he asked me, do you think that there could be an application of duality? Do you see some kind of duality in matrix models? And at that time, I was working on the two matrix model. And I was precisely working on some duality that, for example, on some papers of Paul Zinjustin, and which was at a very heuristic level at that time in random matrices. But the main idea is that when you have a two matrix model, if you study the integrable system corresponding to the first matrix and the integrable system corresponding to the second matrix, somehow they should be the same integrable system. They should be the same tau function. But proving it in a mathematical way was not so easy, as it proved later. But basically, this was the start of our interaction with John. And when he asked me this question, I said, of course, there must be in random matrices. It's the ideal ground for testing that. And John invited me to spend some time at CRM, and I say 2.5 years. And this was really great years. We wrote many papers together, also with Marco. And I interacted a lot with also Jacques, with Dima, and many other people. I can't see the faces here in the room, but I'm sure there are plenty of other people that I know. I don't know Michel or okay.
Olivier Marchand is also here.
Oh, Olivier is here. Okay, I can't see. The faces are too small on the screen. So with John. We wrote 7 papers together. So the first few were about proving that matrix integrals are actually the isomorphic tau function in the sense of Miwa-Jimbo. And this was very good papers. Then in the second part, we reproved this duality in the two matrix model. And it was a very good series of papers as well. And then I re-interacted again with John more recently about Hurwitz numbers. Weighted Hurwitz numbers, and we had another great series of papers, and I hope I didn't forget it. Now let me go to my talk more properly. So the plan of my talk, so I'm going to talk about some geometric way of considering tau functions and in relation to the moduli space of flat connections on bundles. So I will start by introducing bundles, the adjoint bundles, their monodromies. I will talk about their deformations, the notion of tau function, and for that, the notion of correlators. I will also look at a connection to W algebras and Virasoro algebra, and I will conclude. These works are based on a long series of things that I've done for a long time. It really started with some paper with Michel Berger, and it's really, so all of what I'm going to talk about is really the heart of the thesis of my student Raphaël Béliard. But I interacted with many other people, in particular, many of these things were discussed with, so we have current work with Jacques Urtubis, but this also came from discussions with many of you, in particular John. So some of it was used in these papers with of its numbers. This was what I'm going to talk about is also really, I mean, it's very close to the topic of when I came for the Eisenstadt chair in 2015, and I was trying to present that, if I had time, many of these things that I'm going to talk about today. So let me start by a very quick introduction on bundles. So a principal bundle is a bundle over, so let me take a bundle over CP1. Okay. Let me take a bundle over CP1, whose fiber is a Lie group, a reductive Lie group, and a holomorphic bundle, which is, so CP1 is contractible. So basically this is a trivial bundle. Okay. The typical examples of such groups are typically GLR or SLR. And here I will, for simplicity, I will consider that the group is represented as matrices in a faithful representation. It makes things simpler. The typical example is SL2, where you have for each X in CP1, you have a matrix psi of X, which is 2 by 2, and whose determinant is 1. Now let me consider connections on this bundle, and let's consider meromorphic connections. So connections that can have poles at punctures Z1 up to Zn. And what we call a flat section is something that obeys nabla psi equals 0. So in equation, it means that the derivative of psi equals A times psi. And some examples are when A has only simple poles. This is called a Fuchsian system. But in matrix models, we encounter very often the case where A is a polynomial. So it has one pole, but of higher degree. It's not a simple pole. But the general case is when A can have as many poles as you want of arbitrary degrees. And this is considered hard. This is called wild. Now let me consider the asymptotics near the poles. So let me recall the formula for A. There is something well known which is called the Stokes phenomenon. So basically, the solution of the differential equation psi equals A. The derivative of psi equals A psi. It is known that it has asymptotics that behave in a strange way near the singularities. So psi has essential singularities, and the asymptotics are different in terms of in which sector you approach the singularity. So there are several sectors, and to find the sectors, in fact, you should look at, I don't know if you can see my pointer, my mouse, can you see it?
Yes, I see.
Okay, so if you look at the largest term, so the term with k equals di, how it behaves on, so A is a matrix, so it has eigenvalues. And in fact, in order to find the sectors, you should look if the direction in which two eigenvalues at large when x is very close to zi, the direction in which two eigenvalues have the same imaginary part. That draws some lines that are the anti-Stokes lines on the Stokes sectors and the other sectors between such two lines. You can write it in terms of root system of your Lie algebra if you want the condition that two eigenvalues are degenerate. And the asymptotics in each sector look like that. In fact, I've probably mostly learned it from John, by the way. So the asymptotics in different sectors, they look like that. And let me explain the various terms. So first, the term psi hat is the term that behaves like identity plus analytic at Zi. The C on the right, the constant C on the right is a constant, and it's piecewise constant in each Stokes sectors. On the fact that this constant is different in the different sectors is precisely what was discovered by Stokes. It's really the Stokes phenomenon. And it's strange that some psi, which is analytic, has a behavior, an asymptotic behavior with some discontinuous quantities. But that's the Stokes phenomenon. Now let me explain what is the T and the V. So the T, in fact, let's not first define the T, but it's differential. dt is basically the matrix, the diagonal matrix of eigenvalues of A of x dx, or really only the leading part of, I mean, the singular part of the eigenvalues. So let me define Y to be the eigenvalues of A of x dx. and V will be the matrix of eigenvectors corresponding to it. So how do you find the eigenvalues? One way is to solve the characteristic polynomial equation. This has several solutions, several branches. Let me call them Yn, and you expand them at x very close to zi as a Laurent series. While here, what I call xi is nearly the same thing as x minus zi, except that when in some cases there can be degeneracies, and you need to take a fractional power of x minus zi to be a good local coordinate. But basically, the eigenvalues always have a negative Laurent part plus analytic. And what we shall keep in the T is the integral of this negative Laurent part. So first, we make a diagonal matrix with the branches. So the different eigenvalues make a diagonal matrix. A diagonal matrix, you should think of it as an element in the Cartan algebra. And it's a differential form. So it's a Cartan tensor differential form. And this is what we call our dt. So in formula precisely, T is the integral of this. So it contains some negative powers of xi and also a logarithmic term, possibly corresponding to a residue. So yeah, so this is what we have. This is the usual behavior near the singularities. Now, let me talk about monodromies on Stokes matrices. So if you make a non-contractible loop, typically because it encloses some of the singularities in the base, then in the fiber, psi may comes back in the same fiber, but maybe with a different value in the fiber. And typically it gets multiplied on the right by a matrix, which is independent of x, and which you call the monodromy. Let's also look at the Stokes phenomenon. Remember that the constant C depends, so around the singularity, it depends in which sector you are. And when you go from one sector to the next, let's also say that you multiply by a matrix that you call S. If you want, S is defined by the C of one sector times the C inverse of the next of the previous sector.
Bertrand, I have a question. Because you write that psi is V Ci of x, but shouldn't it be independent of x and speed if you put the x dependent in psi hat?
Well, the way I define it, it's not independent. It's the vector. It's the matrix of eigenvectors of the leading part of A of x dx.
Oh, the whole matrix of eigenvectors is okay. I see.
Yeah. Okay. Well, sometimes people include it in the definition of psi hat, or I mean, okay, it doesn't matter much. It's just a way of writing. Okay. So let me. Yeah. So there is another type of monodromies. It's related to this T0, because remember, the matrix T here has a logarithmic term. And this logarithmic term was related to the residue of y. And so because there is a logarithm, and when x goes around the loop, the logarithm takes a phase 2 pi I. It means that the psi will be multiplied by this matrix, exponential 2 pi I times the diagonal of the residues. So I also consider this to be part of a monodromy. And typically in Schlesinger systems or in Palovesics or things like that, this is really what is called the monodromies, these quantities. And so altogether, they form what I call the monodromy data. Okay, let me now go to let me recall a little bit the Miwa-Jimbo isomondromic deformation theory. So what is called the Miwa-Jimbo tau function. So let me recall that. So first of all, let me define psi formula. There is a problem. Psi. I hear double.
Yeah, it's somebody was unmuted.
Okay. So psi formal is basically the same as psi, but without the C in the right-hand side. So either you take psi and multiply it by C inverse, or it's the same thing, you would replace C by identity. And this psi formal is now the same in all Stokes sectors. But now it does not correspond to the asymptotic of an analytic function. But the advantage is that it's the same in all Stokes sectors. And it's a formal series. This psi is a formal series. Now what Miwa, Jimbo, but also in papers with Ueno, Takasaki, I mean, all these Japanese schools define, and what they remarked is that the following quantity is a closed form. Well, first, let me remark that the delta here refers to deformation. So it refers to a cotangent vector in the moduli space of these connections. Whereas here, the D, and that's why I use a delta letter instead of a D. The D here is the differential on the surface on CP1. So the D is a differential on CP1, whereas the delta is a differential in the moduli space. So it is a closed form as a differential in the moduli space. And so thanks to this D, I can take the residue. So the residue of a one form, because it's a one form. And I take this psi formal times psi formal inverse. Since these are matrices, I can take the trace, you take the residue, and the claim of Miwa, Jimbo, and all that is that this is a closed form. Yeah. So, and remember that the delta T here was this diagonal matrix, and remember that it contains the delta of the times, T is the I case. Here we assume that it is an isomonodromic deformation. So we are considering only deformations, for example, that don't include the term k equals 0. So, or if you want, we assume that delta with k equals 0 is vanishing. We can also deform the position of the poles, which is usually what people do in Schlesinger systems, on the times where these residues. So, and since this is a closed form, you can write, it can be considered as the differential, locally it is the differential of some function, which you call the tau function, or more precisely the log of a tau function, and this is really the definition of the Miwa-Jimbo tau function. So it is the function whose differential is equal to this closed form. Let me recast it in a slightly different way. Let us use that d psi was equal to a psi, and use the cyclicity of a trace to put the a on the left, and then on the right we have psi formal delta t psi inverse. So you will see in all the next slides that this kind of thing, psi something psi inverse, will appear all over the place. So we shall study it in more details now. So this leads me to talk about the adjoint bundle. The adjoint bundle is also a bundle over CP1, but now the fiber is the Lie algebra. And the connection on this bundle is the adjoint connection, which is again D minus A, but where A acts by the commutator in the Lie algebra. And let me introduce this definition, which, well, I denoted M of X dot E. There exists other notations in the literature. For example, Goldman writes it sigma instead. Okay. Well, which is basically psi E psi inverse. And this is an element of a fiber above the point X, of a fiber of the bundle above the point X. And let us compute its derivative. Let's compute the derivative of M with respect to X. And it's very easy to derive this formula. It's a two-line computation. And just observe that if E is constant, if it does not depend on X, so if d over dx equals 0, then this implies that M satisfies this equation, which is really the same thing as writing that the nabla of M is 0. So M is a flat section of the adjoint bundle. And so, in fact, every flat section of the adjoint bundle is an M of XE with E fixed. Okay. Let's talk about the monodromies. We know the monodromies of psi, and M is defined in terms of psi, so it's very easy to find the monodromies of M in the adjoint bundle. So when psi goes, when you go around the loop, psi gets multiplied by S, and for M, it means that the E gets conjugated by the monodromy matrix. So it's the adjoint action of the monodromy on E. On the Stokes sector, so if we look at the asymptotics near Zi, we see we shall see how it gets changed. So first remark that in M we have psi times psi inverse. So which means that we'll have somewhere exponential t and exponential t inverse. And exponential t is something with an essential singularity near the pole, and exponential minus t will have the opposite exponential behavior. And let's look at what it means. So let me write it in this way. If I write M for some E, in fact, let me conjugate the E by C minus 1C. And so some of the terms will have exponentials and some will not. And in fact, for that, the best is to decompose E, or more precisely, the C minus 1 EC, into the space. Let's use the space root decomposition of the Lie algebra. So, which means that every element of the Lie algebra can be written as an element in the Cartan plus a sum of elements corresponding to the root spaces. And when you do that, the Cartan, in fact, the Cartan by definition, it commutes with, so since T is also in the Cartan, and the Cartan is a commutative algebra, the element of the Cartan commutes with the exponential, and so the exponentials in the Cartan, they cancel. So the terms in the Cartan has no essential singularity. It is an analytic expansion near the poles. And the terms in the root spaces have an exponential corresponding to various roots. So this is the behavior of M near the singularities. Now let's look at general deformations, not only isomondromic. Let's look at any deformation. For that, let delta deformation, and let's start by looking at the deformation of a flat section, so delta psi. And let me define delta psi times psi inverse, and let me call it f of x. And our goal will be to compute it now. So let's first look at some of its properties, and in particular monodromies. The fact that psi has monodromies, in fact, implies that f has monodromies as well, and the monodromies of f are additive. And you recognize that you have a psi, delta S inverse, type psi inverse. So this is an M. This is an M where the E that you have inside the M here is delta S inverse. So it's the deformation of a monodromy. Let me write it this way. So, okay. Now let's look at the behavior near poles. We know the behavior of psi. So let's compute the behavior of F near the poles. It contains several terms. So there will be the deformation. So you see there will be the deformation of T, the deformation of C, the deformation of psi hat, the deformation of V. So we'll have 4 terms. Let me write all of them. But they are of slightly different nature. First term, the delta T, look, this is again a psi, something psi inverse. But remark that this is not a constant function of x. It's a meromorphic function of x. Where there is also the delta C, which is really now again an M, a little bit like this one. And it's very similar to this one, but with the Stokes matrices instead of the monodromies. And the other terms are basically analytic at Zi. So let me put in this way. So this term, as I said, is an M with the E inside here to be the deformation of Stokes matrices. And this term contains C-1 delta TC. And remember that delta T was related to the deformation of the times, and in particular, the isomondromic times. It's the same, it appeared also in Miwa-Jimbo, this one. Okay, so now what we are going to do now is to use Cauchy formula. So we are going to write that f of x is the residue of f of x prime dx prime over x prime minus x, because this is just a tautology here to write this Cauchy residue formula. And the residue is an integral around a small circle where x prime runs along a small circle around x. And let me deform the contour. For that, let us choose a point here, anywhere, a generic point in the plane, and let's draw some lines from this point O to the various singularities. And let's cut this. And let's also cut small circles around the singularities. And what remains will be a simply connected domain. Let us call it the fundamental domain. And we shall deform, so we had an integral around some x here, and we shall deform the contour in such a way that now the new contour will go to the left of each edge around the circles, and then to the right of each edge. So here is the formula that it gives. Well, for simplicity, I ignore the case where there is a pole at infinity in CP1. So 2 pi I times f of x is the sum of the integrals. So here we have the integral along the left side of an edge minus the integral around the right side of the edge and the integrals around the small circles. But in fact, for the small circles, let me take a sum of arcs for each subsector. So I have a sum of arcs for each subsectors here. And let us now use the fact that we know the monodromies. In particular, the value between two sides of an edge is the same thing as the monodromy corresponding to going around that edge. So if I have an edge E, let me call it E perpendicular the monodromy around that edge. And the difference of the two F's is an M of the delta SS inverse. And for small circles, now let me use the asymptotic behavior of F near the singularities. So we have this term with the delta T, we have this term with the delta C, and we have these terms that are basically analytic at the ZIs. And in fact, they will disappear when I will shrink the circles to radius 0. So the last line will mostly disappear when the radius of the circle tends to 0, which I will do later. So this is what we have. So for that, you see that we had to compute integrals of some, we had, in many places, we have to compute some integrals of some M with some, basically, and as I said, so this is a flat section in the adjoint bundle. So we had to take integrals over some contours in the adjoint bundle that correspond to flat sections. This notion was introduced in particular in the papers by Goldman and with discussions with Jacques Urtubis. I think he told me that it should be called local coefficient homology cycles. So let me, so it's probably a little bit sketchy here, but let's consider the homology valued in the bundle, in the adjoint bundle, in the Lie algebra. Let me define, so if you want, the picture that you should have in mind is that the CW complex for this homology is made of, you take some Jordan arcs in the base, and you lift them to flat sections in the bundle, in the adjoint bundle. Let me define, as Goldman did, the boundary operator. The boundary operator is whenever you have a boundary, a chain that has a boundary in the base, you look at all the values in the fiber, and the boundary is 0 if all the values in the fiber add to 0 in the Lie algebra. Okay. Goldman also defined a symplectic structure, which is an intersection, and basically it's the intersection in the base times the bracket, the Lie algebra scalar product in the fibers. And this is a symplectic space. Now, let me say that it is possible to integrate some quantities along those cycles in the bundle. What you want to integrate are some forms that have a dx. So they are one forms in the base tensor, something in the algebra that can be contracted with something that can be contracted with the Lie algebra in the fibers. So you want something that lives in the adjoint of the Lie algebra, the adjoint bundle. But such forms can be integrated in such contours. So this was much used in Goldman's works and many others. But in fact, they mostly consider the case where these forms are holomorphic. Now, what I will need is to generalize this a little bit with meromorphic. So I will allow omega to have singularities at the ZIs. And this changes things a little bit. And let me write the pairing as an integral. So what we have seen in the previous slide is can be rephrased using these notations. What we have seen in the previous slide is that the f of x was just an integral of the m divided by x prime minus m on such a generalized cycle. And this generalized cycle is made, remember, it's a sum of edges with the flat section corresponding to the delta SS inverse. It has also this term, which is the sum over the arcs corresponding to the Stokes sector of the C-1 delta C. And it has also this term with C-1 delta T C. This term is not constant. It's not a flat section. However, it is well defined in the dual space of this flat of a connection of the forms. Okay, I don't want to enter the details, but there is so this is really the notion of generalized cycles. It means that you allow also things that are not constant, that are not flat sections. And this can be paired now to meromorphic quantities. Now, an important feature is that this indeed has boundary 0. And the way to prove that it has boundary 0 is really to use the fact that the product of all monodromies around the contractible cycle equals identity. It uses this. And also, this is important to know that the boundary is 0 because the condition that the boundary is 0 is precisely what tells you that this integral over gamma delta does not depend on how you choose your base point O and how you cut the plane into some fundamental domain. It's independent of that, and it's precisely the condition that the boundary is 0, which tells you that. So, so now let me introduce another quantity which is very useful, which are called the correlators. I will just give a definition that we introduced with Berger in 2009, and we made a series of papers about that. But it may seem very strange, this definition. You may wonder why we make this definition. It is motivated by random matrix theory, because it's really the natural object to look at in random matrix theory. And it also appears in topological recursion, but maybe mostly because topological recursion was also motivated by random matrix theory. So here is the definition. So let's define first W1. W1 is the trace of A times M. You can write it in a more intrinsic way as the scalar product of A dx times M, or you can also remember use that, use the cyclicity of a trace, and you can also write it in this way, which you see here, there is the Maurer-Cartan differential form. So this is the definition of W1. We also define W2 in this way. We take the trace of M at point x1, e1 on M on another flat section x2, e2, and we multiply by this quantity that has a double pole. Just let me observe one thing here. I could multiply two matrices that belong to different fibers of the bundle. I can do that because this is a trivial bundle. If the bundle would be not trivial, the formula would be more complicated, but here for simplicity, I restrict to trivial bundles. And then we can also define W3, which is a product. You see, you have M of x1, x2, x3, or in a different order, M with 1, 3, 2. And in general, Wn is the sum of our permutations of all possible orders of the M's and divided by product of xi minus x sigma i's. And in fact, you should take only the permutations that have only one cycle. And this is also a differential form. So you may wonder, why is this definition useful? It is useful because it is useful in random matrix theory, and I will show in the next slides that it is also useful in general for every integral systems. These WNs have appeared in many works, and it's at the heart of the thesis of Raphaël Bédiard. And also, it played a very important role with the paper of Berthollat, Brovin-Young, who applied this to KDV and to intersection numbers and to algebraic geometry. So this is used nowadays in many other things. I just cite a few papers, and just let me mention that we also used it in our papers with Eynard on the Harvest numbers. So let me go now to the next slide. So what we have shown so far is that we can compute F as this delta psi as an integral of M along this kind of generalized cycles. So let's look now at the deformation of the correlators of the WNs. First, it's very easy to compute the deformation of W1. You reuse the definition of W1, you apply. So in fact, I used the lax equation to arrive to that, but it's easy, it's the easy part, it's well known. And then let's now, you see here that in this equation, you have a psi E psi inverse. So you recognize an M and you have a differential of F, and the F is written here, you take its differential. Now, the only place, so the D here refers to the differential with respect to the variable X. And the only place where X appears is in the denominator there. So when you differentiate, it will create a dx over x prime minus x to the square. So this is the formula that you get. And let's now exchange the trace on the integral and gives that, which you recognize as being the W2. So what the result is that the deformation of W1 is an integral of W2. And it's easy to do it for every n. The deformation of Wn is always the integral of Wn plus 1. In fact, this kind of property is very important in algebraic geometry or in string theory, for example. It's very well known as it has the name of special geometry property. It plays a very important role. So we see that our Wn's have this property, so which means that they are nice objects. Okay, let me go to the next slide. So I just showed you that the deformation of W1 is W2. And now let me, so there is a result of flatness, which is that if you do two deformations of W1, it's independent of the order in which you did the deformation. And let me sketch the proof a little bit. So when you compute delta 1 of delta 2 of W1, so you're computing delta 1 of this integral of W2. And the deformation of W2 itself is an integral of W3. And you have to keep in mind that the gamma here, my generalized cycles, it itself depends on the, you see it has this delta t, it itself depends on the moduli. So it has a deformation. It can have a deformation. So there is another term by Leibniz rule, which is the integral of W2 on the deformation of gamma. Now, if you make the difference, well, let me skip that. If you make the difference, you have an integral of W3 minus another integral of W3, but in the where you exchange the order of integrations, and plus an integral of difference of integrals of W2, which I write as only one integral, but with the commutator of the cycle. So which means I take the commutator in the fibers. So remember that W3 has simple poles. And the difference of orders of integration of W3 is in fact exactly picking the residue at the simple poles. And the residue at the simple poles is exactly W2 on the commutator. So basically, this means that this is 0. So this is the proof of the theorem. And now the fact that that there is this flatness condition is exactly the condition that there exists locally a function that we can call tau, the tau function, whose deformation is the integral of W1 on gamma delta. So there exists such a tau function. If the delta was only containing the isomondromic part, so if the gamma delta would contain not this term or not this term, but only this term with the delta t's without the terms k equals 0, if there would be only that term, in fact, this equation would exactly be the Miwa-Jimbo tau function. And in general, when you contain the other terms, in fact, this differential here, this differential form on the right, is in fact the Bertholin-Malgrange differential for the more general cases. And so basically, this is the tau function that you find in matrix models. This is really the tau function. So what we have seen so far is that there is a relationship between deformation. So each time you have a deformation, you can associate to it a generalized cycle. In fact, this map is invertible, and the inverse map is very simple because every time you have a cycle, you will associate a deformation, and you define it by seeing how it deforms the flat section. Because once you know how to deform the flat section, you know how to deform everything else, because everything else can be written in terms of flat sections. In particular, the connection is easily found from the deformation of flat section. So you just apply the same formula. And so it means that to every generalized cycle, you can associate a deformation. Let me use that to define a very special case. So let me consider a very specific type of generalized cycle, and let me take this generalized cycle. So let me choose an x in the base in CP1, and an e in the fiber in the algebra, and let's take a small circle around x, multiply by a simple pole, and divide by 1/2 pi I, and weighted by this e, and I mean take the flat section corresponding to this e in the bundle, and let's take this deformation and tensor it with a dx. So this will be a deformation tensor one form, this insertion operator. The main property it has is that when you apply it to Wn, you find Wn plus 1. The proof is in fact very trivial, because remember, by definition, a deformation acting on Wn is an integral of Wn plus 1 with a small circle around x times a simple pole. And basically, it means it's exactly picking the residue. So it's exactly evaluating Wn plus 1 at this point. So I mean, in fact, this equality is very trivial to prove. It's almost by construction. And this means that you can write the flat connection on the moduli space of your connections using this operator, and the delta, which is now the nabla, sorry, which is now a connection on the moduli space, can be written as delta minus gamma delta paired with delta. And in formula, it's just exactly what we wrote before, that the deformation of Wn is the integral of Wn plus 1. So it is the pairing of delta Wn with gamma delta. It's just the same formula as before. And in terms of the tau function, it just says that the delta operator acting on the tau function gives W1, which justifies that we should call the log tau, we could call it W0, by the way. So it's nothing different from what I wrote before, it's just new notations. However, this notation is very useful if you want to study the property how the Virasoro and W algebra appear. I see that I'm close to the end of my time, but I'm nearly finished. I have 2 slides, basically.
Yeah.
So first, I will not define carefully, the Casimirs. The Casimirs are elements of the enveloping algebra of the Lie algebra G, and they are basically tensor products of elements of G, and which belong to the center. So which means they commute with every EI in G. So the Casimirs, and they are multilinear combinations written in a basis. So let me be sketchy about how to define the Casimirs. And so once you have the Casimirs, let's now define this operator, Wk of x. So let's take x in the base, point x in CP1, and let's define this operator. So it's the insertion operator taken at x, weighted by by basically all the possible elements of your basis. And let's take this multilinear combination that exactly corresponds to the Casimir. It's also useful to introduce a generic function for all the Wk's. Let me call it W of xy. And you just take a sum over k from 0 to the rank of your, to the dimension of your representation of your Lie algebra, of your Lie groups. Yes, so the dimension of your representation with -1 to the k, y to the r minus k wk of x. And if you think of it, for example, in GLN, this is just in some sense, very closely related to the characteristic polynomial. So it extracts the x corresponding to the eigenvalues, and you take. Okay, let me a little bit sketchy. So one property, so almost by definition, how does this WK acts on log tau, for example? When it acts on log tau, it will take this multilinear combination with the Casimir coefficients of Wn evaluated at this x of ei1 up to x of ein. Remember that this is the same x everywhere. And remember that, in fact, Wn has simple poles, so you need a small regularization when you have simple poles, but basically this is but this combination is in fact well defined. Okay. So now the theorem is the following. Wk, when it acts on tau, gives something meromorphic as a function of x in CP1. And let me say that this is not trivial because remember that each Wn was a combination of m's, and m is psi e psi inverse. Psi has essential singularities at the zi's. So you have a big combination of things that have essential singularities, that have possibly exponentials and essential singularities at the zi's. But this precise combination with the Casimir coefficient has no essential singularity. It has no exponentials. And this is not this is not so trivial from the definition. It has to be proved, but this is true. This is a theorem which we made with Berger, Borot, and also Béliard, Marshall. Okay. Well, we can be even a little bit more precise if we use this this generating function Wxi. We apply it to tau and divide by tau. The right-hand side is something that is meromorphic in both x and y. It's a polynomial of y, and basically it's a rational fraction of x, and it's nearly the same thing as the characteristic polynomial of our connection y of a of x. It's nearly the same thing. Sorry, I forgot the dx. So it's nearly the same thing plus some other algebraic terms, and well, I speak only for the people who understand what I'm talking about, but terms that are only strictly inside the Newton's polygon. Okay. And this theorem is in fact the same thing as what is usually called loop equations in matrix models. Let me mention something that goes back to when I was in Montreal, and especially with Marco Bertola. So in the case of a two matrix model, if you apply this, you find that the right-hand side is the prime 1 of x minus y times the prime 2 of y minus x minus this expectation value. And this, in fact, Marco had conjectured this formula. I don't know how he made this conjecture. He told me that he tried the V1 and V2 up to degree 5 or 6, I don't remember, and he had observed that it was always true. And he did not have a general proof. We found the general proof with Berger much later. It took like 5 more years to find it. But now it's proven. And let me just say that it's really non-trivial. I don't know any trivial proof of that. And even in the one matrix model, in fact, this was known before, but even in the one matrix model, the proof is not easy. Okay. I'm almost finished. I wanted to talk a little bit about semi-classical limits. So what happens when you put a small parameter? In fact, many people call this small parameter h bar, and they talk about classical limits compared to quantum. In fact, in the work of Dubrovin and Krishever and all that, this small parameter should better be called the dispersion, and it should better be called the dispersionless limit, I think. But some people call it the quantum parameter, and some people call it like dispersion. It doesn't matter here. So basically, it consists in rescaling. So basically, this small parameter limit is like taking a very large A. So you rescale A by 1 over h bar, and it could still depend on h bar. But let's assume that it has a let's assume that it has a limit h bar going to 0 times 1 over h bar. The connection gets so there is the rescaling connection, and in fact it's better to introduce the notion of an h bar connection because we put the h bar in front of the d now, so we multiply everything by h bar. Now, being a flat section is the flat section equation gets an h bar in front of the derivative, so it's just the same equation with an h bar in front of the derivative. what we call on same thing for the adjoint. What we call now the classical spectral curve will be so the classical spectral curve. Let me define it as taking just the limit of A, the characteristic polynomial of the limit of A. It is not exactly the same I defined before earlier in this talk. It's another one, but somehow they have the same limit when H bar goes to 0. And again, Y is a diagonal matrix. And if you think of it, Y takes values in the cotangent space tensor the Cartan algebra. And this is really what is called a spectral curve. In fact, the good notion should be to talk about the cameral cover, which is what I learned from Jacques Urtubis. In fact, we are working on that with Jacques Urtubis. So all this should be formulated in the cameral cover. I'm just simplifying things here for this talk. Now, what happens when you take the asymptotics at h bar to 0? At least heuristically, we see that M, again, the M contains, so when you decompose E on the root spaces, the Cartan part, in the Cartan part, the exponentials disappear. So this part the Cartan part has a limit when h bar goes to 0. The other terms have exponentials. And let's decompose the root space into the positive Borel part and the negative Borel part. In the positive real part, we take only the roots such that the real part of this exponential are strictly positive. And this has no limit when h bar goes to 0 because it is exponential of something with a positive real part very large. It has no limit. Whereas for the negative Borel part, this exponential has a limit. It tends to 0. It tends to 0 faster than any power of h bar. So if you want all your formalism to have a limit, so basically you should look at only the cases where E contains no positive Borel part. So you should better study the WNs with only some E's that have no positive Borel part if you want to have a proper limit. On the negative Borel part, you don't really care about it because it will vanish exponentially faster than any power of h bar. So if you are interested in the asymptotic, perturbative asymptotics in powers of h bar, you can ignore Borel parts and you can work only with the Cartan parts. So in some sense, in the semi-classical limit, all the adjoint bundle somehow tends to localize on its Cartan part. And the Cartan part of the adjoint bundle is in fact more or less the cameral cover. So what you see in this framework is that asymptotically, when h bar goes to 0, you see how all this framework becomes really the notion of spectral curve, and the loop equations imply topological recursion, and you see the topological recursion naturally appearing in this framework when h bar goes to 0. So many of these things are yet to be proved. It's really more heuristic. And by the way, this is a work in progress with Jacques Urtubis and Raphaël Béliard. Let me conclude my talk. So first, you see there is a really beautiful geometric structure in integrable systems on the fact that we can associate deformations to these cycles. And cycles have intersections. Cycles are much more topological objects or homological objects. So it's much easier to understand things in terms of these cycles. And also with this method, we really recover all the known things about tau functions. For example, everything in randommetry theory fits in this framework. We also, with Ribot and Chekhov, we try to apply this framework to conformal field theories. And for example, if you take SL2 with 3 singularities on Fuchsian, then you exactly recover that the tau function, you can compute the tau function exactly with this method. So we just have to compute the integrals over these generalized cycles. This is doable because the psi's are some hypergeometric functions. So all integrals can be computed. And using that, you exactly recover the DOZZ formula for the tau function. And also this picture, this framework allows to understand heuristically quite well how things transform to a spectral curve in the H bar going to zero limit. And all of these things, I mean, many of these things about integrable systems, I must say that I learned them by talking with John. And you see, many of these works have something in common with also what we did with what Bertola, Dima, Korotkin, and with John, with Jack, and many others. And I want to thank you, John, and I want to thank you all for your attention. So, do you have? Did I lose you? Is there any question or? It seems that the sound is not working anymore. I cannot hear anything.
Okay.
Okay.
Can you hear me?
Hi.
Hi. Nice to see you. Nice to see you, Bertrand.
No.
I have a question also, of course, it's partially was in our activities related to this stuff, but nevertheless, so when we are considering monodromies, there is this difference between, say, monodromies that we have on the Riemann surface, in which we can basically expand into some basis of finite dimensional basis of cycles.
Mm-hmm.
And here I think we cannot make it this way, right?
I'm not sure what you mean, but the dimension of the space of generalized cycles is infinite. It's an infinite dimensional space.
Yes. So, for instance, we cannot define some theta function based on it, right?
Well, yes and no. Okay, I mean, the tau function is not a theta function, for sure.
Yes, tau function is not theta function.
Okay,
right?
so when you speak about these generalized cycles, there are generalized cycles. So the usual generalized cycles that are finite dimensional and that correspond only to the holomorphic part, they are indeed finite dimensional. And you can consider them as first kind, and they correspond really to what you would call the deformation of the filling fractions in matrix models. And there is a finite number of them. And you can take a sum over all the filling fractions, and it will define indeed a theta function, a kind of theta function. But in fact, in the formula for tau, you also need the part that corresponds to not only the first kind, but also second and third kind. But there you don't really have to sum over filling fractions in some sense. I don't know if I answer. Oh, I mean, it would be. I would like to discuss this more with you, but
yeah, me too. No, I just mean that possibly there is no very good answer to it.
Well,
okay.
There is no short answer to it, I would say.
No, sure. Yeah, that's true. Okay, because I was waiting for John to ask questions. So that.
Yes, but well, we have a technical malfunction.
I could not hear.
Can you hear me, Bertrand?
Yeah.
Okay, just a very small point. I couldn't follow all the details of what you were doing, but a lot of it was familiar. But at one point you were talking about the Casimir functions.
Yeah.
But you didn't say what the Poisson structure was.
Well, here I'm talking about the Casimirs of the Lie algebra. So the element of the centers of the Lie algebra.
Yes.
The enveloping algebra.
Yes, but there's no loop algebra there, right? It's just an ordinary finite dimensional algebra.
Yes, it's inside. So it's not on the bundle here. It's only in the Lie algebra itself.
Okay. So okay. When Marco gives his talk on Friday, there will be some other Casimirs which you'll probably recognize, but that has to do with the loop algebra. So I thought,
I think these are related to the Hamiltonians.
Yes.
There
Yeah,
are small motions of Casimirs in the story. I didn't talk about that, but they are there too, of course.
okay, very good.
But
So-
yes, we can write the Hamiltonians here.
Okay, so thank you for beautiful survey talk.
Jacques?
Just a comment on Leonid's question. If you're considering the abelian case, the space of connections plus line bundles would be some sort of affine shift of the cotangent bundle of the Jacobian, the spectral curve.
Yeah.
Now, the theta functions live just on the Jacobian.
Yeah.
The analog for this case would be probably, again, an affine shift of the cotangent bundle of the moduli space of bundles.
Yeah.
And so the theta functions would be just on the moduli space of bundles, would ignore the cotangent directions. And that there's a big theory. It's the things that are given by the Verlinde formulae. They're these holomorphic sections of theta. They're called generalized theta functions, in fact.
As a paper by Fay, actually.
Yeah, and I think this is more or less the answer to Leonida's question, by the way.
Yeah, no, that's what I was saying. It's I think that's the place where you look at these things.
Yeah, exactly. Yeah, I think you're totally right. And in fact, yes, the claim is really that these things are exactly the conformal blocks. And this is why we studied, by the way, the Virasoro operators.
Conformal blocks, that's the word I was looking for. Sorry.
Yes. So these are the conformal blocks. And basically what we wanted to check. So I forgot to say it in my yes, what I wanted to say is that basically all this formalism satisfies exactly all the axioms of conformal field theory. So all the bootstrap axioms. So the fact that the W's have poles, have simple poles, and W2 has double poles is exactly the OPE in CFT. The fact that the Casimirs give something that is meromorphic is exactly the Ward identities. And then there is then checking the crossing symmetry is in fact exactly integrability. And then you have also fusion rules, normally in the axioms of Bootstrap. And this is what we have not finished working on, it's the fusion rules. But yes, this is totally equivalent to a formalism of Verlinde and the others.
Okay. Thank you, Bertrand. Any other question? I had a question, but unfortunately I have to escape because I have to teach. So I will ask you the question.
Me too. So I apologize. I have a class in 5 minutes. So.
Okay.
But let's thank the speaker.
Okay. Thanks a lot. It's so good to see you again.
Glad to see you.
And